Imagine teaching AI to truly understand the web of relationships that shape our world. Social networks, molecular structures, the internet itself. But what if we could simplify the way AI learns these connections, making it faster, smarter, and more adaptable? That's exactly what Graph Prompt aims to do. Today, we'll explore how this groundbreaking approach is changing the game for graph neural networks. Let's dive in. Graph neural networks, or GNNs, have been amazing at learning patterns from graph data. But here's the problem. They're like students who can't learn without an exact study guide. They rely heavily on large, labeled data sets tailored for specific tasks. That's expensive, inefficient, and just plain frustrating. For example, the discrepancy between pre-training and downstream tasks causes inefficiencies in transferring knowledge, leading to suboptimal performance. Inefficiency of fine-tuning demands substantial labeled data, which is not always available. Limited applicability of existing prompting methods, which are either restricted to specific tasks or unable to generalize across different downstream tasks. Enter Graph Prompt, a revolutionary framework that bridges the gap between pre-training and real-world tasks in a way GNNs have never seen before. Inspired by prompting methods in NLP, Graph Prompt uses a clever approach to unify these tasks, making AI smarter, faster, and more versatile. This graph from the paper shows exactly what problem Graph Prompt will solve. This figure from research paper shows exactly how it works. Instead of training GNNs separately for every task, Graph Prompt uses subgraphs as a common thread. During pre-training, the model learns relationships using tasks like link prediction. Then comes the magic, learnable prompts that adapt this knowledge for specific tasks, like classifying nodes or entire graphs. It's like giving your AI a flexible toolkit, ready to tackle any challenge with ease. Specifically, Graph Prompt solves the identified issues in the following ways. Graph Prompt aligns pre-training and downstream tasks under a unified framework using a shared task template based on subgraph similarity learning. By framing both pre-training tasks and downstream tasks in terms of computing the similarity between subgraphs, it bridges the gap between these stages. This unified representation ensures that knowledge from pre-training transfers effectively to downstream tasks, minimizing discrepancies. Instead of fine-tuning the entire GNN model for each downstream task, Graph Prompt introduces learnable prompts, lightweight, task-specific parameters that guide the downstream task to utilize the pre-trained model effectively. This eliminates the need to update the GNN weights, significantly reducing computational overhead and improving efficiency. The learnable prompts focus on extracting task-relevant knowledge from the pre-trained model while keeping the rest of the model frozen. Here's the accuracy comparison from the research paper comparing to other state-of-the-art methods. Graph Prompt employs learnable task-specific prompts to customize the readout operation used for aggregating subgraph information. This ensures that the aggregation process focuses on features most relevant to the specific downstream task, improving performance by aligning the extracted subgraph representations with task objectives. For example, node classification prompts emphasize local node features, while graph classification prompts consider global subgraph patterns. This is a quick look of the algorithm. The algorithm for designing and fine-tuning Graph Prompt helps tailor a graph-based prompt for specific tasks using a pre-trained graph neural network. It begins by initializing a prompt vector and a loss function, which guides the optimization, which is in line 1. The algorithm then uses the pre-trained GNN to compute node embeddings, representations of nodes in the graph that capture their structural and feature information, which is in lines 2, 3. For each tuning sample, the algorithm accumulates loss values to refine the prompt, which is in lines 5, 13. Specifically, it creates a prompt designed for the given task, which is in lines 5, 6, and calculates subgraph representations for class prototypes, which represent each category or output class, which is in lines 7, 8. These representations are used to compute a task-specific loss, which is accumulated across samples to update the overall objective function, which is in lines 9, 13. Finally, the algorithm optimizes the prompt vector by minimizing the loss, improving its performance for the given task, which is in line 14. This process ensures that the prompt is fine-tuned to guide the GNN effectively for the target application. The complexity of a graph-based algorithm, particularly one using graph neural networks, can be broken down into a few components. First, to calculate embeddings, or representations, for a node V in the graph, we consider the node's average degree D, the typical number of connections a node has, the number of GNN layers K, and the size of the embedding D. The complexity for this embedding calculation is ODDK, meaning it scales with the embedding size and the number of neighbors processed across K layers. Additionally, extracting the subgraph around a node for computation depends on the number of hops required to include neighboring nodes. This process has a complexity of ODD, reflecting the number of connections involved within these hops. Combining these, the overall complexity to compute embeddings for a node subgraph, including a readout operation, which summarizes graph information, is ODDKDD. Importantly, when techniques like neighborhood sampling are used, where only a small subset of neighbors are considered at each step, DD becomes a small constant, significantly reducing the computation cost and making the algorithm more efficient. But no innovation is perfect. Graph prompt still faces hurdles. The learnable prompts, though effective, are abstract and not easily interpretable. Unlike handcrafted prompts or direct feature-based models, their internal workings can be opaque, making it challenging to explain or debug the specific role of the prompts in task adaptation. This can be a concern in applications requiring high transparency, such as healthcare or finance. Although Graph Prompt is designed for few-shot learning, the learnable prompts still require careful tuning. In cases with extremely limited labeled data, there is a risk of overfitting the prompts to the small sample size, especially if the prompt design introduces too many parameters relative to the data. Graph Prompt's reliance on subgraph similarity learning as a unification mechanism may not generalize well to all types of graph tasks, such as dynamic graph analysis, graph generation, or tasks that involve edge-specific objectives. Extending the framework to handle such non-standard tasks would require significant modifications. While Graph Prompt introduces computational efficiency compared to fine-tuning, the extraction and processing of subgraphs for tasks involving very large graphs or high-dimensional features could still be resource-intensive. This could limit scalability in applications with extremely large-scale graph data, such as web-scale social networks or knowledge graphs. These caveats highlight the importance of careful implementation, evaluation, and possible enhancements to Graph Prompt to ensure its applicability across a broader range of use cases and its robustness in varied settings. Graph Prompt isn't just a step forward for AI, it's a leap. By uniting pre-training and real-world tasks, it's setting a new standard for how we train intelligent systems. If you're as excited about this breakthrough as I am, hit that like button, subscribe, and let's unravel more tech wonders together. Thanks for watching.